Hey everyone, welcome to Medfoxes. In this Cardiac Pacemakers a Beginner's Guide series, we're going to discuss cardiac pacing leads. If you've already watched my video on pacemaker battery technology, you're probably familiar with the basics of pacemakers. Now, let's dive into pacing leads.
Pacing leads must perform continuously in a very hostile and active environment. The salt content of human blood is similar to seawater and equally as corrosive. In addition, the lead itself must withstand pressures from bones and ligaments, plus at only 70 beats per minute. A lead will flex 100,000 times a day, 37 million times a year, and almost half a billion times in a year. This core pace lead module addresses the design and performance factors that allow leads to operate effectively in this environment. This slide illustrates the essential components of pacing leads, which include conductor, connector pin, insulation, electrode, lead assembly. In following slides, these essential components will be discussed separately. The conductor is a very thin wire that carries electrical impulse from the pacemaker to the distal tip of pacing, or carries intracardiac signals from tip electrode to the pacemaker for sensing. The wire, commonly made of MP3-5N nickel alloy, must have very low resistance to allow efficient transfer of energy from the pacemaker to the lead tip, thereby helping to minimize energy need for each impulse from the battery. Physically, the conductor must flex millions of times without breaking. There are three types of conductor commonly used in leads. They are unifilar, multifilar, and cable. A unifilar is a single wire coil that is wound around a central axis in a spiral manner. Coiling the wire helps to facilitate flexibility without breaking. A multifilar conductor consists of two or more wire coils that are wound in parallel together around a central axis in a spiral manner. This construction helps to reduce impedance in the conductor and builds in redundancy in a filar wear to break. A cable conductor consists of two or more wires that are twisted together as a strand and then bundled with other strand around each other like a rope. Most leads today as unifilar constructions. So, if one or more filament fracture, the other fracture will still pace and sense. In this situation, intermittent sensing and pacing may occur, signaling a possible lead problem. Leads are constructed as unipolar, bipolar, or multipolar, depending on how many conductors are present to complete the pacing electrical circuit. Today, almost all unipolar leads uses multifilar construction with multifilar coil surrounded by insulation. Let's see the characteristics of unipolar lead construction. The unipolar leads are smaller in diameter because there is only one conductor coil and the insulator between the two conductor coil is eliminated, and it is less rigid also. It is due to one conductor coil and one layer of insulation. Apart from these limited advantages, there are many other disadvantages exist, which include the unipolar leads produce large spacing spikes on ECG. Since the electrodes are located at relatively larger distance from each other, it detects the surface EKG signals are usually larger. Another disadvantage of unipolar lead construction is susceptibility to oversensing and extracardiac stimulation. The former is due to the time it takes intracardiac signal to traverse the relatively large distance between electrodes. An extracardiac signals that appears at either electrode could be detected by the indifferent electrode. Older IPGs were also susceptible to extracardiac signals, but today modern IPGs have sense filters to avoid this problem. The extracardiac stimulation pacemaker current flows between the electrodes encompasses extracardiac tissues. Muscles near the pocket site sorry muscle stimulation near the pocket site is due to current flow associated with electrical current at indifferent electrode in the pacemaker. Next in our lead construction, we have bipolar lead. Today, the most common bipolar lead construction is coaxial, where an insulated layer separates two multifilar conductor coils positioned in concentric fashion. A new bipolar leads today uses co-radial construction. This is also called parallel wound, where two insulated coils are wound next to each other. The following slide demonstrates some additional bipolar construction types, which include parallel coil and coil cables. Some bipolar leads uses parallel coil construction. This illustration shows two coils in parallel. Some bipolar leads uses combination of coils and cables. The coil facilitate the passage of stylets for lead implantation and pacemaker and placement, while the cable facilitate a smaller size lead body. In this slide, we can see the characteristics of bipolar leads. Historically, bipolar leads had large diameter. They have become smaller due to coaxial conductor design, advanced insulation design, which are thinner, and smaller conductor coils and cables. The second conductor coil and insulation between the conductor coil makes the bipolar lead stiffer. A softer tip-to-ring spacer is used in many lead designs to make the distal tip more flexible. Compared to unipolar leads, bipolar lead have shorter distance between the tip electrode and indifferent electrode, which reduce susceptibility to oversensing non-cardiac signals. This distance also reduces the likelihood of extracardiac stimulation of muscles near the IPG pulse generator. Most bipolar pacemaker can be programmed into unipolar electrode configuration as well. This feature provides more flexibility. For example, to observe a larger spacing spike on surface EKG. Bipolar leads are less likely to produce muscle and phrenic nerve stimulation because of the smaller electrode field, that is tip to ring versus tip to cane. In view of material, most conductors today are made of MP35 and nickel alloy. This material offers low resistance to electrical current. In addition, it is corrosion resistant, flexible and durable. MP35 and silver cord conductor have the same performance characteristics as above, but offer enhanced conductivity. The next component of lead is connector. It connects the pacing lead to the IPG. An accurate mechanical fit between the connector pin and the pin cavity of pulse generator is crucial. for the safe transmission of current from pulse generator without current leakage. IS-1 is a formal international standard for pacing connector developed jointly by International Organization for Standardization and the International Electrotechnical Commission in 1992. Both bipolar and unipolar IS-1 lead connectors are 3.2 mm in diameter and have a sealing rings and a short connector pin. Sealing rings provide proper insulation of the pacing lead electrical connection. The leads are labeled IS-1 uni or IS-1 bi. You will also notice that unipolar connector have a blue connector ring as a visual indication that the lead is unipolar. Prior to IS-1, other lead sizes include 3.2 mm low profile and 5 by 6 mm. These connector sizes are only seen today during IPG replacement. In this case, adapter may be required. In this slide, let us see the insulation of pacing lead in detail. Insulation is non-conducting material that prevent electrical current from escaping into the tissue surrounding leads. Insulations also protect the conductor from corrosion due to exposure to the body fluid and tissues. An implanted transvenous pacemaker lead may be subjected to a variety of loading forces in the human body, which may lead to insulation damage. Therefore, insulation material should be flexible, durable, and have low friction. The properties shown in the following slides helps define insulation behavior. Ideal insulation material should have following properties: includes tensile strength, elongation, tear strength, abrasion, compression set, cruise due to the cyclic compression, and creep. Types of insulation include silicon, polyurethane, and fluoropolymers. Silicon and polyurethane are most commonly used insulation material for pacing leads. Silicon is a soft, flexible material and has been used over 30 plus years in pacing leads. It is used for outer and inner insulation in today's pacing leads. Currently, silicon is used on half in the world pacing leads. Polyurethane is firmer, stiffer material than silicon and had been used over 20 years for pacing leads. It is used for outer and inner insulation in today's pacing leads. Currently, polyurethane is used in half of the world pacing leads. Fluoropolymers, that is PTFE, polytetrafluoroethylene, and ETFE, ethyl tetrafluoroethylene, is a soft, stiffer material and is used primarily as a coating to protect conductor wires from corrosion. In addition, fluoropolymers are used to make the conductor more slippery, so as not to cut through the primary silicon or polyurethane insulation. Fluoropolymers are used in less than 5% of pacing leads today. Silicon rubber has been used for more than 30 years as a pacemaker lead insulation. They are inert, which means structural composition is chemically inactive. Biocompatible, which means does not initiate an inflammatory rejection response, and biostable, which means structure and material remain relatively unchanged. In vivo. On the other hand, the disadvantages of silicon include the silicon is sticky, which means high friction coefficient, means that silicon is not inherently slippery, and handling damage, because silicon is more prone to damage from abrasion, surface nicks, and cuts. Attention to handling is impressive. Although nicks and cuts can be repaired with medical adhesives. Size. Some type of silicone leads tend to be larger in diameter than polyurethane leads because has less tear strength. There are different types of silicon that have varying characteristics. For example, the new Metronic 4719 silicon has a greater tear strength and resistance to crush and creep than silicon and or HP silicons. In this slide, we can see the advantages of polyurethane insulation of leads. The polyurethane is biocompatible, means it does not initiate an inflammatory rejection process. It has high tear strength, means tougher and resistant to damage by abrasion, surface nicks and cuts. It has low friction coefficients and less fibrotic, means the slippery surface reduce platelet addition. And last, the lead diameter of polyurethane is tougher and can be applied thinner than most silicon. In addition to several advantages, the polyurethane also had a notable disadvantage like environmental stress cracking and metal ion oxidation. Environmental stress cracking is crazing or cracking polyurethane insulation due to the in vivo environmental exposure and internal stress. Environmental stress cracking can sometimes result in complete break or crack through the insulation material. Metal ion oxidation is oxidative degradation of polyurethane insulation. Here, the body's natural defense against the foreign object produce cells, macrophages cells that produce peroxidase. The peroxidase migrate through the polyurethane. You can see in this slide, this picture, and and the oxygen molecules from the peroxidase mix with metal ions from the conductor. This mixture works to oxidize the polyurethane. In this example here, metal ion oxidation has occurred to the point where the polyurethane insulation has completely oxidized and broken away from the lead of this side. In this slide, we can see another insulation materials, fluoropolymers advantages. These materials are coated with PTFE, polytetrafluoroethylene, and ETFE, ethylene tetrafluoroethylene, around the conductor wire or cable. The fluoropolymers are inert, most biocompatible, and has high tensile strength. Newer silicon and polyurethane lead allow for thinner insulation in many models, which makes the lead body diameter smaller and facilitate these benefits, which include small introducer size, easier insertion, passage through small vein, more flexible lead bodies. Two lead can go through one introducer, less intrusive.
That wraps up part 1 of this topic in cardiac pacemakers, a beginner's guide. Link to part 2 of this lecture is in the description. Head over there to continue your learning journey. And when you're ready to test your understanding, visit our website to access two powerful assessment tools: a comprehensive knowledge assessment featuring over 500 MCQs based on the entire video series. An IBHRE style exam simulation consists of 5 blocks, 40 questions on each block, timed to help you sharpen your time management for the real exam. These assessments are ideal for board exam candidates and healthcare professionals alike, whether you're aiming for IBHRE, CCI, EHRA, or just want to solidify your rhythm management expertise. Check the description for all links and start challenging yourself today. If you're enjoying this series, like, share, and subscribe to Medfoxes. It really helps us grow and reach more learners. Thanks for watching, and I'll see you in the next one.